When we think about the future of robots, the really exciting stuff, it's not just arms on an assembly line. It's more about these general purpose helpers, right? Robots that can actually adapt and learn and help out pretty much anywhere, a factory, sure, but also like a hospital or maybe even in your house.
Exactly. And that whole vision, it really hinges on robots becoming incredibly versatile, but actually training them for that kind of diversity. I mean, for countless different tasks in totally different settings. And this is key across lots of different physical robot bodies, what we call embodiments. Well, that's the huge hurdle.
Right. It's just so complex when you think about it. How do you teach a skill, let's say picking up something delicate that one robot learned in a lab? How do you transfer that know-how smoothly to a totally different robot? Maybe one with a different kind of hand, maybe one that moves around in a messy real-world place.
Yeah, and traditionally that's needed just mountains and mountains of very specific data. Every single tiny movement the robot makes has to be labeled like move this joint exactly this much, apply this specific force.
Uh-huh.
And getting that action labeled data is just incredibly expensive, super time consuming. Every time you have a new robot or a new task, you're often starting pretty much from square one, collecting and labeling.
It really limits things, doesn't it? It's this fundamental bottleneck stopping robots from learning faster and, more broadly.
It's like trying to teach a kid how to walk by giving them precise angle commands for every joint instead of just showing them, hey, walk over there.
Exactly. So the problem isn't just getting them to work, it's scaling it up. We've got just tons of video data out there, internet videos, people doing things, security footage, but almost none of it comes with those neat little robot action labels. So yeah, how do we actually use all that information?
And that brings us nicely to today's deep dive. We're going to focus in on a research paper and some related thinking about a system called UniVLA, that's Unified Vision Language Action. And it looks like a really significant step towards kind of breaking through that data bottleneck, towards creating these truly generalist robot policies.
Okay, UniVLA. And the big promise here you're saying is that it can learn from basically any video, even just unlabeled clips of humans doing stuff, and then apply that learning across different robots.
That's the core idea, yeah.
All right, so for this deep dive, our mission is basically to unpack how UniVLA works. We really want to get into its main innovation and figure out how it manages to learn more efficiently and generalize better using these, well, surprising kinds of data.
Okay, let's unpack it. So, this journey towards robots learning from all sorts of data, it's been moving really fast. If you look back maybe before, say, 2018, getting different kinds of robots, different physical designs to learn from each other, this robot transfer idea, it often involved really fiddly manual work. You literally had to map out how actions on robot A matched actions on robot B, sometimes joint by joint.
Which sounds incredibly brittle, like it wouldn't scale at all.
Exactly. It was pure custom engineering for every single pair of robots. Then, with the huge boom in large language models and vision models, we started seeing these vision thousand action models, VLAs, popping up in robotics. That was really kicking off around 2019, 2020.
Right, the VLAs, trying to connect what the robot sees and what it understands from language commands to the actual actions it needs to perform. And we saw these big data sets emerge around then too, didn't we? Things like Ego 4D with all that first-person human video, RoboTurk using crowdsourcing, Salvin for complex sequences, and those big multi-robot data sets like OpenX embodiment.
Yeah, those data sets were absolutely crucial. They gave us the scale needed to train these bigger, more capable VLA models. Systems like RT1, Octo, OpenVLA, they really push things forward. But even with all that progress, even with these massive data sets, there was still this fundamental catch. They mostly relied on videos that were specifically collected with robots and, crucially, had those detailed ground truth action labels.
Ah, okay.
They were clever about using large language models, often by kind of turning continuous robot actions into discrete tokens the LLM could process, but you still needed that initial labeled robot action data to train them.
So even the advanced VLAs were still stuck with the labeled data problem. Which brings us back to that key question you raised earlier. What if somehow we could learn a single unified action representation? one that isn't tied to any specific robot's hardware.
And this is where I think it gets really interesting. UniVLA proposes a pretty fundamentally different way of tackling this. Instead of trying to predict specific robot joint commands, or even just turning those commands into tokens, they focus on learning a unified, embodiment-agnostic latent action space. Learning it directly from videos, and here's the kicker, without needing those explicit action labels.
Okay, hold on. Latent action space, let's break that down. Does that mean it sort of watches a video and learns to capture the gist of the action, what's happening regardless of who or what is doing it?
That's a great way to put it, exactly. Imagine watching a video, maybe someone opening a drawer. A latent action model tries to capture the drawer going from closed to open and boils it down into a compact code, maybe a vector or a specific token from a set. It's not recording the exact finger movements or the force, but the task relevant change, the outcome. It's distilling the essence of the action.
That sounds really powerful. But you mentioned this idea isn't totally brand new. Other systems like Genie, Lapa, Igor, they also tried learning latent actions from video. What was the issue there?
Yeah, they ran into a pretty major snag noise. If you just tell a model, hey, learn a compact code for all the visual changes you see between these two video frames, it captures, well, everything. Not just the drawer opening, but maybe the camera shaking slightly, the lighting changing, someone walking past in the background, other objects moving that aren't part of the task. It all gets crammed into that single latent code.
Ah, I see. So the code wasn't just open drawer. It was open drawer plus OS camera wobble plus OS background movement plus maybe a cat walking by.
Pretty much. And that kind of noisy, cluttered, latent representation makes it incredibly difficult for a robot policy to learn reliably. It's trying to figure out how to act based on a signal that's full of irrelevant junk.
Okay, so UniVLA's challenge was to figure out how to filter out all that noise, how to capture only the action that actually matters for the task. How do they pull that off? This feels like the real academic core of their work.
It really is. Their key technical idea is this novel two-stage training framework. It's specifically designed to decouple the task-centric visual changes from all the task-irrelevant noise. They wanted a latent space focused purely on the changes relevant to achieving a goal.
Right, decoupling. Two stages. Walk me through stage one. How does it learn to spot the irrelevant stuff first?
Okay, stage one. They train a model, let's call it the latent action model. Its job is to predict what the scene will look like a moment later, given the current scene and a latent action code. But here's the crucial twist. The model is also given a language instruction that describes the overall task. So if the video shows someone picking up a red block and the language instruction is pick up the red block, the model sees the video frames and that text instruction.
Okay, and how does giving it the language instruction help filter out the noise?
It comes down to the capacity of that latent action codebook in stage one. They deliberately constrain it. It can only represent a limited amount of information. Now, because the language instruction, pick up the red block, already gives the model a strong clue about the main task relevant change. The model learns to use the language information primarily to predict that main change. The limited space left in the latent action codebook then gets used almost by default to encode all the other visual changes happening, the stuff not directly covered by the language instruction.
Huh. So if the language tells it about the red block moving, the stage one latent code is sort of forced to represent everything else, like maybe the lighting shifts a bit, or the camera jiggles, or another block in the background gets slightly nudged.
That's the really clever insight. By using language to handle the main task prediction and limiting the latent code's bandwidth, stage one effectively pushes the encoding of all that task-irrelevant visual noise into that first constrained latent space. So those codes become the vocabulary for task-irrelevant dynamics.
That's fascinating. It's like using the language as a filter or a spotlight. And stage one learns to represent everything outside the spotlight. Okay, so what happens in stage two?
Right. In stage two, they take the model they trained in stage one, keep its parameters, but they freeze that task-irrelevant latent action codebook they just learned. It's fixed. Now they introduce a completely new set of latent actions, a second codebook. The model gets trained again to predict future visual states. But this time, it can use both the frozen task-irrelevant actions from stage one and this new set of actions it's currently learning.
Okay, so it already has codes for the noise, thanks to stage one being frozen. What are these new actions optimized to capture then?
These new latent actions are trained specifically to encode the task-related dynamics, the core movements, the object manipulations, the purposeful changes that actually align with the language instruction. Because the noise encoding is already taken care of by the frozen stage one codes, This new set of latent actions can focus entirely on capturing the essence of the goal-directed action itself. This explicit decoupling is what allows them to get a much cleaner, more focused, truly task-centric representation of the action.
That makes a lot of sense. It's like teaching it what to ignore first, then teaching it what's important, using a fresh set of tools, knowing the noisy stuff is already accounted for.
Precisely. And there was another really key technical decision they made that helped this whole process quite a bit. Instead of trying to predict raw pixels in the future frame, which, as we said, are full of distracting details like textures, exact lighting conditions, etc., UniVLA uses something called DINO of 2 spatial patch features as both its visual inputs and what it tries to predict.
DINO's 2 features, right? Those come from self-supervised learning on tons of images, don't they? They're supposed to capture more about objects and spatial relationships.
Exactly. DINOS 2 is a vision model pre-trained without labels, and its features capture these more robust, high-level visual concepts. They're more object-centric, more aware of spatial layout than just raw pixel values. It's an idea inspired by work on JPIA, joint embedding predictive architectures, which learn by predicting abstract representations, not pixels.
Ah, okay. So by using these richer DINOF 2 features, the visual information the model deals with is already less noisy and more focused on the kinds of things that usually matter in a task, objects, their shapes, where they are relative to each other.
Precisely. So you combine that two-stage decoupling framework with the use of these more meaningful DINOF2 features, and that's how UniVLA manages to learn this discrete codebook of task-centric latent actions. Codes that represent meaningful changes, generalize across different robots and views, and are effectively filtered from all that visual noise.
Okay, fantastic. So they've created this vocabulary of clean task-centric latent actions. How do they actually build the robot policy, the generalist policy that uses these actions?
Right, so now they have these learned latent action codes, which they can get by processing pairs of video frames through their trained latent action model. They essentially treat these codes as pseudo-labels. They become the target output that the main robot policy needs to learn to predict. The generalist policy itself is built on a powerful vision language model base. Specifically, they used one called Prismatic 7B. It fuses inputs from strong visual encoders SIGLIP and DINO2 and connects them to a large language model backbone, in this case LMA2.
Got it. So instead of the policy spitting out, say, raw motor commands or even those discrete bins for motor ranges like some older VLAs did, it predicts sequences of these learned latent action codes.
Yes, exactly. They actually extend the vocabulary of the large language model, adding special tokens to represent each of the possible latent actions from their learned codebook. The policy then effectively plans by predicting a sequence of these latent action tokens, one after the other, autoregressively based on the current image, the language goal, and the previous tokens.
That sounds, well, a lot more abstract and maybe manageable than predicting fine-grained physical movements directly.
It provides a really significant efficiency boost. Planning in this compact, compressed latent action space is just computationally much, much lighter. Think about the numbers. UniVLA's latent action space might have something like 16 to the power of 4 possible discrete actions based on their codebook structure. Compare that to some prior approaches like OpenVLA, which might dispertize, say, 7 degrees of freedom each into 256 bins. You end up with a massive space like 256 to the power of 7.
Wow, yeah, the combinatorial explosion's way smaller.
Exactly. And that efficiency directly impacts training cost. They reported achieving really competitive results with dramatically less pre-training compute, something like only 120th of the computational cost compared to training OpenVLA from scratch. That's a huge deal for making these kinds of generalist policies more practical to develop.
Okay, so the main policy predicts this sequence of abstract latent actions. But how does a real robot, a physical arm or a mobile base, actually do them? How do those abstract codes turn into volts going to motors?
Yeah, that's handled by a separate, much smaller, lightweight module they call the decoder. For each specific robot, you train a small decoder. Its job is to take the sequence of latent action tokens predicted by the main policy and translate them into the actual physical control signals, the joint angles, the gripper commands, whatever that specific robot needs.
Ah, so the big complex generalist policy stays high level and totally robot agnostic, while the specific how to move my joints knowledge for each robot is contained in these little separate decoders.
That's the architecture. The decoder might use something like attention to look at the current visual features, understand the context, and then maybe a simple linear layer maps the latent action token to the right motor commands for that specific robot. And this setup makes it much easier to adapt the system to new robots. You train the main policy once, which is expensive. Then, for a new robot, you mostly just need to train its small decoder, often using techniques like LoRa parameter-efficient fine-tuning, which only adjusts a small number of parameters.
That sounds incredibly useful for actually deploying robots in different situations without massive retraining.
Yeah, it makes adding support for a new robot body much less painful. Oh, and they also incorporated another clever idea to help the policy handle tasks that require multiple steps, sequential reasoning. It's inspired by the chain of thought prompting seen in large language models.
Oh, really? So instead of just remembering what it saw recently, what does it feed back into itself?
It feeds back the historical latent action outputs. So the latent actions what the policy predicted it was going to take in the last few time steps, it incorporates those predicted latent actions back into the input prompt for the current time step. Instead of feeding in, say, the last few raw video frames, which are high dimensional and contain noise, it feeds back this compact semantic summary of its own recent intentions or plan.
Huh. So it remembers its own recent plan in this latent space rather than just a visual memory.
Exactly. It gives the policy a kind of short-term memory of what I just tried to do, encoded efficiently using the latent action tokens. They found this really helps it reason better about the next steps needed for longer, more complex tasks without the heavy computational cost of processing lots of past image frames.
Okay, so we've got this novel way to learn task-focused latent actions, using smart visual features like DINO of 2, a VLM policy planning efficiently in this latent space, and these lightweight decoders for specific robots. Plus this chain of thought-like memory. How does it all stack up? Does this academic ingenuity actually translate into better robots?
Well, the results they presented look really quite strong. They definitely seem to validate the overall approach. UNVLA was tested across a whole bunch of benchmarks, complex manipulation tasks in simulators like Libero, Kelvin, Simple M, and even navigation tasks like RTR. And importantly, they also tested it on actual physical robots.
Okay, let's get into some specifics. How did it compare to, say, the previous state-of-the-art like OpenVLA?
It showed pretty significant performance improvements across the board. On the Libero manipulation benchmark, for instance, UniVLA hit an average success rate of about 95%, which was nearly 19 percentage points higher than OpenVLA.
Wow, 19 points is huge in robotics.
It really is. And for the R2R navigation task, the gap was even wider. UniVLA outperforms OpenVLA by almost 30 percentage points. Then in their real-world physical robot tests, UniVLA showed around a 37% improvement in success rate over the next best baseline method they compared against.
Okay, those are seriously impressive numbers. What do they tell us about why it's working so well? Do they confirm the core ideas?
Yeah, I think they tell us a few key things. First, they really validate the idea of data scalability. The performance consistently improved as they added more diverse data sources. And crucially, that included adding a large amount of action-free human video from datasets like Ego4D. This really seems to prove that their latent action learning method is successfully pulling out useful, actionable information from these unlabeled videos, which was a major goal.
So the dream of learning by watching humans actually seems to be working here, enabled by this latent action framework.
It looks like it. Second, the results strongly support the idea of data efficiency during adaptation. It's not just that it can learn from diverse data. UniVL can also adapt to new situations or tasks using remarkably little specific data for that new task. On one tough benchmark, Libero-Gar, they showed UniVL achieving better results than OpenVLA while using only 10% of the downstream fine-tuning data.
Only 10%. That's a massive advantage for practical use. Less data collection, less labeling time, less cost.
Absolutely. And third, the results also validate the quality of the learned latent actions themselves. They showed examples where the same latent action code seemed to represent similar kinds of visual changes even when performed by different robots or seen from different camera angles. That confirms the embodiment agnostic idea. And quantitatively, they did experiments comparing policies trained using their task-centric latent actions, the ones from stage 2, versus policies trained using only the task-irrelevant ones from stage 1, or actions learned using simpler methods without their special decoupling process.
And I'm guessing the task-centric ones won out?
Significantly so. The numbers, especially on the harder, longer tasks, clearly showed that the policies trained with the decoupled task-centric latent actions performed much, much better. That's strong evidence that their two-stage method really is filtering out the noise and capturing the part of the action that matters for learning. They even showed visualizations, like attention max, where predicting a latent action correctly makes the model focus its visual attention on the robot's hand and the object it's interacting with.
That's compelling evidence. How did it fare in the real world with all the unpredictability compared to simulation.
The real-world tests were important. They showed UniVLA was pretty robust to things like variations in lighting, unexpected clutter appearing in the scene, and even handling objects it hadn't explicitly seen during training. While a policy trained only for one specific task might be perfectly tuned for that single motion, UniVLA's advantage seemed to be its broader understanding of the task goal, allowing it to adapt to variations. It did particularly well on tasks needing sequences of actions, or maybe needing to replan if something went slightly wrong, like stacking blocks. And importantly, because it plans in that efficient latent space, it could run fast enough for real-time control on the robot, avoiding some of the inference latency issues that have plagued some other large VLA models.
Okay, it sounds genuinely impressive. But like anything in research, I imagine it's not the final answer yet. What are the main limitations they acknowledge? Where does it still fall short?
Yeah, absolutely. The authors are quite upfront about the current limitations. One is that the granularity of the actions is kind of fixed by the size of that discrete code book they learn. Maybe for really fine-grained manipulation, you want actions that can be represented at different levels of detail, perhaps hierarchically. Also, most of the demonstrations and evaluations focused on tasks with a single robot arm. Scaling this up to control more complex systems like robots with two arms working together, or maybe dexterous multi-fingered hands, would likely require modeling a more complex, possibly higher dimensional action space.
Makes sense. And while it's amazing it can learn from action-free video, that core decoupling process you described, stage one, it still relies on having language instructions paired with those videos, right? To know what the task is.
That's a key point, yes. To separate the relevant changes from the irrelevant noise, it uses the language instruction as the signal for what should be considered relevant. So while it can leverage big data sets like Ego4D, those videos still needed some form of language annotation or task description associated with them, at least for that initial latent action learning phase. Truly tapping into, say, completely uncurated YouTube videos might require future work on maybe automatically inferring the intent behind the actions or generating descriptions automatically.
Okay, so building on this work, where do they see it going next? What are the exciting future possibilities I mentioned?
Well, one really interesting direction is potentially integrating this latent action model with learned world models for more advanced planning. Since the decoder part of their system can predict future visual states given a latent action, they could potentially use this predict sequences of latent actions internally, simulate the outcomes in this learned future state space, and plan much further ahead without actually moving the robot.
So the robot could kind of imagine the results of different plans. If I do latent action A, then latent action B, all within this compact latent space before committing to a physical move.
Exactly. Exploring plans in that abstract, low-dimensional space is way more efficient than trying to simulate in raw pixels or needing detailed 3D models of the world. And maybe one of the most exciting, almost sci-fi possibilities they touch on is using this to directly encode human demonstration videos.
Wait, so taking a video of like me assembling something?
Yes, taking that video and running it through the trained latent action model to translate your movements and the resulting visual changes into their learned vocabulary of latent action codes.
And then a robot could potentially just take that sequence of latent codes and execute them using its own specific decoder. It could learn the skill just by watching my video.
That's the incredible potential they point towards enabling genuine zero-shot skill learning directly from observing human actions. If they can truly bridge that gap, translating complex human movements into a universal robot action language, that would be utterly transformative for how robots learn.
Wow. Okay, so wrapping this up, it really feels like UniVLA's core idea, learning these task-centric latent actions directly from video, figuring out how to separate the signal from the noise, tackles a fundamental roadblock in robotics. By creating these clean, abstract, robot-agnostic action codes, it seems to unlock the potential of using all this diverse video data out there that was previously hard to leverage for training robots.
It definitely feels like a powerful step towards robots that aren't just programmed for one factory line or one specific body, but can genuinely learn to act effectively across many different situations, tasks, and physical forms, learning from the richness of the visual world.
And it leaves you with this really provocative thought, doesn't it? If we can actually distill complex physical actions, whether done by a giant industrial arm, a little wheeled bot, or a human hand, into these universal latent codes. And if we can transfer these codes between different embodiments, what does that really imply for the future of robot learning? Could we see robots acquiring incredibly subtle, dexterous skills just by, watching YouTube tutorials, essentially, interpreting them through this shared action language? What kinds of new capabilities does an embodiment agnostic action representation truly unlock for robotics and AI?